Welcome, good evening. Welcome to Mount Cuba's public night, virtual public night number, I don't know now. We're up there. If there are no further questions before that, I'm going to go ahead and let Judy introduce our host for the evening, and then we'll get started. So, Judy?
All right. For those of you who don't know me, I'm the resident astronomer at Mount Cuba Observatory, and I have a University of Delaware observational astronomy class that meets just about every semester. And this winter, we had like 11 students, and Doug Andrews was one of my students over the winter session, and he did a very good presentation about space weather. And he's a senior. No, he's a junior/senior/advanced engineering student at the university. And so I invited him to do a public night for us. And here he is. So I'm going to turn it over to Doug now.
All right, thanks, Judy. Let me go ahead and share my screen here and we can get started. Yeah, so I'm going to talk a little bit about the Carrington event and some more general information about space weather. It's helpful to get some background on space weather to understand what went on with the Carrington event and to realize kind of the magnitude of everything that happened. So first, I'll give some background on the sun. So this is not going to be a comprehensive background on the sun, just how it relates to space weather and the Carrington event. So it's basically a ball of hot plasma powered by fusion. And because it's a ball of hot plasma, it's you can kind of think of it like a whole bunch of hydrogen bombs going off. And this creates a lot of magnetic fields. And those magnetic fields aren't stable. It's kind of a turbulent mess. So you can see here on the left, there's solar activity. There's a solar cycle that happens every 11 years. And there's a solar maximum and a solar minimum. So the image on the left here shows the magnetic field lines on a solar minimum. And magnetic field lines, if you've ever seen like the representation of like a bar magnet or something, you get those lines that go around it. They go from north to south. That's basically what the images here are showing. So the left is a solar minimum, and then the right is a solar maximum. And you can see how organized it gets in a solar minimum relatively and how messy it gets as a solar maximum. Like I said, this happens every 11 years. And what causes this is actually the magnetic north and south pole of the sun switch. So you can see as on the right there is the poles are kind of switching around and rotating. So currently we're in solar cycle 25. There's a maximum coming in the year 2025. So we're kind of in the middle right now. And one of the things that happens with a solar maximum is you get a lot more sunspots and a lot more severe space weather. So space weather, it's like weather, but it's in space. It's a little bit more accurate term could be solar weather because it's caused by the sun. When we're referring to space weather, we're referring to it in our solar system. So it's caused by the sun, and it's comprised of a few different components. There's a solar wind, there are sunspots, solar flares, coronal mass ejections, and coronal holes. And I'll give some background on each of those. So the solar wind is a bunch of charged particles that come streaming out of the sun. And they come streaming out of the corona, which is the outermost part of the sun's atmosphere. And it goes at about 400 kilometers per second, or it's about 1,000,000 miles per hour. And it's basically like a wind of charged particles that radiate out from the sun in all directions. This is a chart of the solar wind here, and you can see it's actually a little bit stronger on the poles and a little bit less strong around the equator, but it's also much more turbulent around the equator. This line here that you see, the red and the blue lines around is the speed of the solar wind around the sun. So you can really see that turbulence around the equator. And it's caused because the temperature of the corona is so high that the sun's gravity can't hold on to these charged particles, so they kind of escape the sun. But we don't really understand many of the details about how all of these gases and charged particles are accelerated to such high velocities. There's a really a lot that's unknown about the causes behind space weather. We kind of observe what happens and see that, you know, one thing may cause another and may coincide with another, but we're not really sure why exactly there. So this image is actually from the Ulysses Solar Wind Plasma experiment, which gives a nice map of the solar wind around the sun. And one area where you might have heard about the solar wind is when the Voyager spacecraft exited the solar system. This is one of the ways that we determined that the spacecraft actually exited the solar system. The Voyager 1 spacecraft, it was kind of a guess because a lot of the detectors on the spacecraft weren't working, but the Voyager 2 spacecraft actually had a detection unit which could detect the effects of the solar wind. So we could determine that it exited the solar system when it detected a sharp drop-off in the solar wind. And there are also sunspots, which are temporary dark spots on the sun that last days to months. They're still really hot and bright. The temperature of a sunspot is about 4,000 Kelvin, whereas the sun's temperature is a little closer to 6,000 Kelvin. And if you can imagine, a sunspot is about 10 times as bright as the moon. So obviously don't look at the sun, you know, just with your naked eye. But if you were able to do that, that's about how bright it would be. And they are concentrations of magnetic flux. So it's kind of just a messy little bit of magnetic flux, kind of those scrambly areas that I showed in the one of the previous pictures of the sun with the magnetic field lines. They inhibit convection, and they usually appear in pairs, kind of like a magnet. There's two of them that would normally be opposite polarity, and they're about 1,500 to 30,000 miles in diameter. And just as kind of a reference, the Earth's diameter is 8,000 miles. So some of these are several times larger than the Earth. However, the sun's diameter is 870,000 miles, so not nearly as large as the diameter of the sun, but just as a reference there. And these actually can be seen with the naked eye. I know if you have ever seen those kind of pinhole cameras that some people use for looking at the sun, if you have one of those and you're really careful with it, you can actually see some of the really large ones with the naked eye. So this is an image of the sunspots here. And they normally occur in bands on either side of the equator. During the solar cycle, they start further from the equator and move towards the equator. So they kind of start towards the poles and move towards the equator. And there's two kind of areas of the sunspot, the penumbra and the umbra. The umbra, you can look at it like with the magnetic field lines coming out of the sun, and the umbra, they kind of go straight towards you out of the screen, basically, if you were to kind of be looking at this picture and imagining the field lines. And the penumbra are kind of when they're curving away. So like if you were to imagine kind of a geyser of magnetic field lines, the umbra would be kind of in the middle where they're coming out towards you, and then the penumbra would be where they're kind of slanted, I guess is a good way to put it. So these were actually noticed a long time ago. They were first mentioned by a Greek scholar named Theophrastus, who was a student of Plato. So back in the BC era, they were first noticed. They were also observed by some Chinese astronomers, but nobody really kind of knew what they were until William Herschel in the early 19th century. He equated sunspots with direct effects on the Earth. He noticed that in the absence of sunspots, England had higher wheat prices, and he actually spoke about this at the Royal Society. But you know, like a lot of people who made pretty groundbreaking discoveries, he was misinterpreted by the Royal Society and completely ridiculed over his papers. So another aspect of space weather is solar flares, which are caused by tangled magnetic field lines near sunspots. These actually occur oftentimes with sunspots, but it's really kind of unclear, kind of a cause and effect relationship with these. It's comprised of plasma accelerated by magnetic energy, but once again, we're not really sure how the magnetic energy is transferred to kinetic energy of the plasma. We're not quite sure how some of these particles can be accelerated to the velocities and the energy levels that they are. But we kind of think that it's due to magnetic reconnection. If you can imagine the magnetic field lines kind of shearing and then snapping back together, they think that, or scientists think that it's kind of has like a rubber band effect on the plasma, which causes these solar flares. And in 1959, actually, Carrington and Hodgson made the first observation of a solar flare, and obviously we will mention Carrington later. So the Carrington event was the first actual observation of a solar flare. So there is a classification of solar flares. And if you look at that image that's hopefully playing for you guys, you can see the solar flare in the foreground as the bright spot, and then there's also a coronal mass ejection that happens in the background as you see that kind of loop that jets out of the sun. So we'll talk about those in a minute. So solar flare classification is done using letters A, B, C, M, and X, and also numbers. It's measured in peak flux in watts per square meter of X-rays by the GOES system. I know that's kind of a mouthful there, but I'll explain.
Doug, can I interrupt you for a second? We do have a question. It says, how were they able to see sunspots 2,000 plus years ago with the naked eye?
So you can, if you see the sun like kind of through those pinhole cameras, like I mentioned, or if you project an image of the sun onto something, you can actually see kind of like little areas where it's a little bit less bright. It's obviously not high resolution, but they did have certain ways to observe the sun other than just kind of staring up at it with their eye.
Thank you.
And that's that. Yeah, that's kind of what I mean by observe with a naked eye, is not staring at it, but if I know we had those filter glasses when we had the eclipse around here. So if you use one of those, you can actually see them when there's a lot of sunspot activity as well. So here's a little explanation on solar flare classification. And this will have some meaning because we'll talk about solar flares and how big the solar flare was during the Carrington event. So it's helpful to know how they're classified. So for instance, with the letters, the number is basically the factor within a letter class. So you can look at it, and A is the least severe and X is the most severe. And then it's, A, B, C, M, or X times 1 through 9. So an M2 flare, for instance, is twice the strength of an M1 flare, and an M3 flare is 3 times as powerful as an M1, but only 50% as powerful as an M2. And it gets a little bit confusing when you go between letter classifications. For instance, an M2 flare is 4 times more powerful than a C5 flare, but there are charts that kind of walk you through how each letter classification relates to the other. So A, B, C, and M go 0 to 9. X actually goes beyond 9. The biggest solar flare ever recorded was during the Halloween solar storms of 2003. This actually missed Earth, fortunately enough, but it burned out sensors on the GOES satellite, which are rated to X28. So the estimate is that could have been a solar flare that measured up to X45 had we had the sensor capacity to measure that. The solar flare in 2003 occurred a few years after the solar maximum. That solar maximum was in 2000. So that was actually a really odd event that we had a really huge solar flare that occurred after a solar maximum. And that flare, that X45 flare, was actually estimated to be similar in magnitude to the Carrington event. So that would have been really bad had it hit us. And we'll go into the effects of if something like that were to hit us in a little while. So there are also coronal mass ejections, which you saw in that little loop in the video on the previous slide. They often follow solar flares, but not always. Once again, kind of cause and effect that's unknown there. So they're caused by particles shot out of the sun, and they take hours to days to reach Earth. Normally, they occur about 3 a day during a solar maxima, and 1 every 5 days during a solar minimum. And these have one of the largest effects on Earth. And they occur all over the sun. So when I say they occur 3 a day during a solar maximum, it doesn't mean that the Earth's hit by 3 of them a day. It just means that somewhere on the sun, 3 of these are occurring each day. The height of them can be multiple times the size of the Earth. So these are really, really big. They also have their own magnetic field. And the large ones can contain 1 billion tons of matter, accelerated up to several million miles per hour. And the fastest ones can reach us in as little as 15 to 18 hours. Some can take days. And one of the interactions with coronal mass ejections, with the time it takes to reach us, is it is actually slowed down by the solar wind. So it's moving faster than the solar wind, and the solar wind kind of creates drag. But if you get to a solar maxima, what happens is a previous flare can kind of cut through that solar wind, kind of like if you were imagining like drafting. And then if you have a second flare that occurs shortly after a previous flare, it's actually not slowed down as much by the solar wind and can reach us much faster. So that's kind of what causes that discrepancy in time there. So here are some images of coronal mass ejections. You can see these are some pretty large ones, and they go left to right. You can see the evolution of the coronal mass ejection. That kind of dark spot in the center of each of them, the little white outline there represents the sun, and that dark spot's kind of a blank, so that you're not the camera's not overwhelmed by the brightness of the sun. And you can see the coronal mass ejections kind of develop over time in these images. And there is a website, www.swpc.noaa.gov, that actually shows you daily images of the sun. So this is an image from earlier today of the sun. We actually do have a little bit of a coronal mass ejection occurring there on the right. So this was a good day to pick to do this talk, because we can actually see some activity in the sun. Normally it's pretty quiet.
Doug, I had another question that came up.
Yeah.
Is there a specific name for the solar flare classification, and do you know who came up with this system?
Actually, I don't. I know that there have been several classification systems that we've gone through, but I don't know if there's a specific name for the current one that we're using.
We can look into that and get back to you, Opal.
And there are also coronal holes. These are, you can kind of look at these as like the opposite of a coronal mass ejection in a way, I guess, as they occur more often during the solar minimum. So they're dark areas in the solar corona, which are cooler and less dense regions in the plasma, and they allow the solar wind to escape more readily. They usually occur around the poles, but can be found at lower latitudes. And this is one of the main causes of turbulence in the solar wind. So this is actually another image from the GOES satellite, which shows the sun earlier today also. The dark areas there are coronal holes. So this is taken in that UV light that shows those coronal holes. And you can also see actually some of the activity on the right-hand side of the image that we saw in that coronal mass ejection slide. So the big question is, what happens when all of this hits the Earth? So the Earth has a magnetic field called the magnetosphere, which surrounds the Earth. It deflects the charged particles from the solar wind and coronal mass ejections. And very importantly, it protects life and electronics from damaging radiation from the sun. So it's currently tilted at an angle about 11 degrees to the Earth's axis. If you look through that first image there, you can kind of see the tilt a little bit. The images at the bottom are a progression of a coronal mass ejection hitting the Earth. So the left is how the magnetosphere looks normally. The middle image is during, say, like a moderate coronal mass ejection, and then the right image is during a very severe coronal mass ejection, kind of similar to something that would be seen during the Carrington event. And you can see how the magnetosphere is really affected by that, and kind of stripped back from the Earth, which on that front side exposes anything predominantly in space to a high level of increased radiation. So it's has very significant effects on satellites, any spacecraft, and astronauts that are in space. And one of the effects on the Earth of these charged particles is the aurora. So it's a disturbance in the Earth's magnetic field from these charged particles of the solar wind, and they excite the atmospheric particles which produce light. So this is actually a little chart of the aurora forecast for tonight, and because of that increased solar activity, there's increased aurora as well. And I've heard the forecast is they could actually be faintly seen as far south as Upper New York. So they're pretty far south today. And at that website listed on the bottom, actually, you can go and see these forecasts daily. So it's pretty neat to look through. And here's another kind of longer term space weather forecast of the last couple of days. So I found this particularly interesting because if you look at the top on the solar X-ray flux there, you can see that little spike in flare class, which happened earlier on February 28th up to the sea level, which actually caused this increase in geomagnetic activity that we're seeing with the aurora and these orange and yellow lines at the bottom showing the geomagnetic activity that's occurring today. So that's a nice little measurement of how long that particular flare took to reach us. All right, so we'll get into the Carrington event, which occurred on August to September of 1859, and it was the largest geomagnetic storm to hit the Earth on record by far. It first began in late August with some sunspots visible to several astronomers over Europe. On August 28th, there was an aurora seen at lower than normal latitudes in places like New England. And astronomers over Europe actually recorded some of the sunspots that they saw. There was a gentleman in Germany called Heinrich Schwabe who recorded these drawings. And then there was a Father Anglio Secchi in Italy who also recorded these. They do look somewhat different because of the optics that each of these particular astronomers were using. Some of them are flipped, and some of them had different ways of recording exactly where they were on the sun, so the orientation is a little bit different. But these have been confirmed to be drawings of the same event of some sunspots. And these are both in their observational logs preceding the event. And then sunspots were also observed by Richard Carrington. I'll show his drawings on the next slide because they are the most detailed by far. So these are Carrington's drawings right here. And of course, his observations are what led this event to be named after him. So he recorded the sunspots and solar flares preceding the Carrington event on September 1st. And they were concurrently recorded by him and a fellow astronomer, Richard Hodgson. Although we don't have detailed drawings from Richard Hodgson, only Richard Carrington. So these are his sunspot drawings, and he actually marks out 4 letters here, A, B, C, and D. And those are actually his first observations of solar flares that occurred at those spots. They actually were 2 solar flares, one which occurred at A and B, and then they moved together kind of towards that C and D as they merged. So he recalled that when he recorded the sunspots, and then when he recorded the solar flares, he obviously saw that he was observing something that was pretty extraordinary. So he recalls that he hastily ran to call somebody to witness the exhibition. Although on returning within 60 seconds, he had found that they had already pretty much disappeared. So this also led to a coronal mass ejection, which traveled to the Earth. It took about 18 hours to get to the Earth. And if you note before, I said that there was some aurora activity seen on August 28th. The predominant theory is that also occurred concurrent with a solar flare, which cleared out some of the solar winds and led to the flare that caused the Carrington event to achieve such great speeds to reach us in about 18 hours. So there are obviously really significant auroras seen during the event. The records show that they were seen in the Caribbean and Hawaii, and it was so bright that it looked like daytime. People recall that newspapers could be read as easily as daylight, and this occurred in the middle of the night. So it was, I believe, about 3 a.m. in the morning when this started. So if you imagine 3 a.m. in the morning and you can read a newspaper while standing outside, that's a pretty bright aurora. The newspapers also recall that there were birds chirping in the middle of the night, and a brick mason crew in South Carolina and also a gold mining crew in the Rocky Mountains got up and went to work because they thought it was dawn at the time. A Boston newspaper said, quote, "The light appeared to cover the whole firmament, apparently like a luminous cloud, through which the stars of the larger magnitude indistinctly shone. The light was greater than that of the moon at its full, but had an indescribable softness and delicacy that seemed to envelop everything upon which it rested."
Doug,
Yep.
I have a question. How did they know to look/measure at that particular time? Sorry, I was off if I missed where you were at.
Yeah, so if you mean the astronomers that noted these things, they were amateur astronomers that basically dedicated their time to observing the sun. So they used their specialized telescopes to kind of look for these sunspots and observe anything that was happening. So they all kind of concurrently noticed this because it was a very large series of sunspots that occurred on the sun. So it was a big event that everybody, or that at least those three, were looking at. Because it wasn't a big field, we don't have wider astronomers looking at these sort of things, because obviously Carrington was the first to see a solar flare. So we just noticed these sunspots and didn't notice that there were any of the other things like solar flares or coronal mass ejections that accompanied those. So one of the effects that the Carrington event had was on telegraph systems. Obviously, in 1859, this was before any sort of electrification, and the telegraph system was really the most advanced electronic system that we had at the time. And the operators of the telegraphs noticed that they received electric shocks while touching the telegraph equipment. And I have a picture of a little, your generic telegraph sender on the left there. And also at this point in time, they had developed a paper recording machine for telegraphs, which I show on the right here, that was developed in about 1840. So it was in pretty widespread use at the time. And a lot of telegraph operators noticed that the paper for these telegraph recorders actually started to catch on fire and would spark. And even, when the telegraph operators noticed this, they quickly unplugged the telegraphs. They operated on a battery. So they thought it was a malfunction in the battery or something, and they disconnected the telegraph system from the batteries. But they found that even when they disconnected them, they could still actually send telegraphs through the telegraph lines, even though they were not powered by any batteries, because they were energized by this event and the charged particles in the atmosphere interacting with the Earth. So, a question comes up of what would happen if something like this were to occur. And we have a couple lesser events in more recent history that occurred. We have the May 1921 geomagnetic event, and then a couple much smaller events which happened during the space age, when we can see the effects on more electronics and that sort of thing.
Can I stop you for 1 second?
Yeah, sure.
The other question I have is, can you explain the difference in the nature of a CME versus solar wind in terms of the material being ejected?
Yeah, so the solar wind is just kind of a constant stream of energetic particles, um, whereas a CME, coronal mass ejection, is kind of a more concentrated, denser group of matter and particles that are streaming towards the Earth. Hopefully that answered the question.
Okay, thank you.
Mm-hmm. So yeah, the May 1921 geomagnetic event was the most intense storm of the 20th century. It also occurred before mass electrification, but we did have some radios operating at the time. This also sparked fires and stopped telegraph service. But one thing a lot of people noticed was that radio propagation was enhanced. So the particles coming from this geomagnetic event, coming from the sun, interacting with the Earth, interacts with the ionosphere, which long-range radio waves bounce off of to propagate around the Earth. So that changes the kind of the makeup of the ionosphere and greatly enhances the radio propagation. And there are some more recent events. In May 1967, there was a geomagnetic event which caused a blackout of a polar nuclear missile surveillance radar. And obviously this sounds really bad, and it was. The U.S. actually started to scramble and prepare for nuclear war until the scientists noticed that this occurred due to a geomagnetic event caused by the sun. There was also a more recent event in March 1989, which brought down the power grid in Quebec. And this is the first example that I found of a geomagnetic event bringing down a large power grid. Normally they're more isolated than this, but this brought down the power grid in all of Quebec. And accompanying this event in 1989, there were auroras seen in Florida and Texas. There were a lot of radio blackouts, and this actually also almost led to increased tensions in nuclear war because the Soviets thought that the U.S. were jamming communications because of that radio blackout. We can also see some effects of satellites in orbit. We lost control of satellites in polar orbits for several hours. And like I said, this brought down the power grid in Quebec because it tripped the breakers that led to we're at the substations of that power grid in Quebec. It actually started cascading due to breakers tripping at a hydroelectric plant. And also there were those Halloween solar storms that I mentioned with that X45 flare, which led to some auroras seen in Texas and a power outage in Sweden. But fortunately, the largest flare from that did not hit the Earth. So this is a little risk assessment that asks, are we at risk for something like a Carrington event? So that graphic on the right was done by Lloyds of London, who's actually done a lot of studies about the effects on the Earth from space weather. Basically, what you can interpret this as is the effect of space weather on the power grid. So anywhere where the dark purple are areas where the power grid could be most affected by space weather, specifically during like a Carrington class event. Any areas that are in dark purple, it's bad news. So unfortunately, that means around us, it's pretty bad news. So this is basically due to the fact that in our power grid, we use the Earth as a kind of a neutral return line. So if the Earth is affected by any magnetic fields, it can actually backfeed into the grid and trip all these breakers. And there are neutral current blocking devices that we can install to stop this, but they're expensive. And obviously, there's a push to try to get power companies to install these, but because it's seen as such a rare event, there's not a huge rush to install these. So Lloyd's predicted that there could be 20 to 40 million people out of power. And some of those could be for years because these power surges would bring down substations. And obviously there's only so many companies manufacturing substations. So they would have to repair each individual substation that was brought down by this, which could be, 12 to 16 month lead time. So there could be areas that are out of power for a year or more. And they estimate the cost from 0.6 to 2.6 trillion. So that could be some really significant damages if a Carrington class event were to hit the Earth. And this is only looking at terrestrial issues. It would obviously affect most all satellites in space. So that would be another huge loss if any of those were greatly affected by such an event. So a big question is, how often does this happen? There's been some studies on the severity of Carrington class event or large, solar flares and large coronal mass ejections hitting the Earth. The University of Warwick and a British Antarctic Survey study stated that there's about a 4% chance of a severe storm occurring every year and a 0.7% chance of a Carrington level event. They used data from the past 150 years and found that a severe superstorm occurred every 42 years out of 150. And a great superstorm the severe superstorm occurred in 42 years out of 150. And then a great superstorm occurred every 6 years out of 150, or once every 25 years. So they pegged the estimate of a Carrington event at about 0.7% probability. But long-term data is kind of hard to come by because geomagnetic data is only available and reliable after about 1868 is when we started recording that data. So some longer-term studies have looked at nitrates and ice cores. And some of the articles that I've seen that talk about the Carrington event online mention the probability of occurrence based on these nitrate samples taken from ice cores, and the nitrates occur because the energetic particles that interact with the upper atmosphere start to fall to Earth and collect in the Arctic and Antarctic, and then can be seen in the ice cores. But unfortunately, those nitrates also come from sources on Earth. So some studies have stated that they're not really reliable because a lot of studies take multiple ice cores, and these spikes in nitrate data that they predict are caused by Carrington class events don't actually occur in all of the ice cores. So any data that's based on those may not be very reliable. And the best predictions that we have are that geomagnetic data starting in 1868. So unfortunately, it's kind of hard to say how often this sort of thing occurs because we've only seen it really once that affected the Earth. We only have a limited amount of data to go off of. Another study that we've done for looking at clues on how often this sort of thing occurs is looking at activity on other stars. So many other stars have sunspots that are even larger than the sun. They also have super flares. So on the left here is some star spots seen on Zeta Andromeda. Zeta Andromeda is a star that's about 15 times larger than the sun. And this was a combination of 6 telescopes that produced this image here. So the dark spots indicate some star spots. Some are near the equator and some are closer to the pole. The 3 that you see closer to the equator there, each one of those is the size of our sun. So those are pretty big star spots that are on this particular star. And super flares also occur on other stars. Normally they're seen on younger stars, but they have actually been seen on stars that are more similar to our sun. There's a star about 1,800 light years away between the constellations of Cygnus and Lyra, which is really similar as our sun in size and age. And it was observed to have a flare that was 10 times as powerful as anything that we've ever seen on the sun. And the Kepler satellite has detected other super flares on other sun-like stars, which could occur every 100 to a few thousand years. So an event like the Carrington event, even though it's the biggest that we've seen on Earth, may not be the largest event that a star like our sun could produce. That's all I have. Thanks.